In the previous video, we have seen how to produce induced EMF or induced current by using Faraday's experiment. Now, in this video, we are going to learn about how to determine the direction of induced current. Now, here, Lenz is a scientist who determined the direction of induced current. According to Lenz's law, the direction of induced EMF or induced current is such that it opposes the change that is producing it. Now if you see the Faraday's two experiments actually, in the first experiment we have seen whenever the magnet is moved either towards or away from the solenoid coil, it is going to induce current. So here, when a north pole is moved towards the front face of the solenoid coil, the front face of the solenoid coil will also develop a north pole. Similarly, if you move a south pole, the front face of the solenoid coil will develop south pole. That means here induced current will be in such a direction that it try to opposes the cause that it produced. Here what is the cause? The motion of the magnet. So the induced current will try to stop the magnet. That's the reason it is going to develop a similar pole. That is, if the current is induced due to motion of the magnet, then the induced current in the coil sets itself to stop the motion of the magnet. If the current is induced due to the change in current in the primary coil, then the induced current is such that it tends to stop the change, which we have seen in Faraday's second experiment. Now, Lenz's law and law of conservation of energy. Here, Lenz's law is going to obey law of conservation of energy. Now, what is law of conservation of energy? Law of conservation of energy is nothing but energy can neither be created nor destroyed, but it can be transferred from one form to another form. Now here the question is how induced current is developed in the solenoid coil. According to Lenz's law, the induced EMF opposes the change that produced it. It is this opposition against which we perform mechanical work in causing the change in magnetic flux. Now here we are moving the magnet towards the coil. Whenever we are moving the coil or the magnet towards the solenoid coil, what will happen? Because of induced current, it develops a similar pole. That means it tries to stop the magnet or the solenoid coil. So we have to perform some mechanical work to change the magnetic flux which is linked with the solenoid coil. Therefore, the mechanical energy is converted into electrical energy. Thus, Lenz's law is in accordance with law of conservation of energy. If, however, the reverse would happen, that is, the induced EMF does not oppose or aids the change, then a little change in magnetic flux will produce an induced current which would help the change of flux further, thereby producing more current. The increased EMF would then cause further change of flux and it would further increase the current and so on without any mechanical work. This would create energy out of nothing which would violate the law of conservation of energy. That's the reason Lenz's law will obey law of conservation of energy. Expression for induced EMF based on both the laws. Now, induced EMF E is equal to minus d phi by dt. Here d phi by dt is represented by Faraday's second law, minus is represented by Lenz's law. So F E equal to minus phi 2 minus phi 1 by t. And for n number of turns of the coil, induced EMF E is equal to minus n d phi by dt. Expression for induced current. Now here we have determined EMF. Now how to determine the current? We are going to use Ohm's law. EMF is nothing but voltage alone. So E equal to I into R. So I is equal to E by R, as E is equal to minus d phi by dt. So we can write the expression as I equal to minus d phi by R into dt. expression for charge. Now, how to determine the charge? We know that current is nothing but rate of change of charge. So dq by dt is equal to minus d phi by r into dt. Now dt gets cancelled, so dq equal to minus d phi by r. Note, induced EMF does not depend on resistance of the circuit, because you can see the expression of induced EMF, there is no resistance, it's just minus n d phi by dt, whereas the induced current and the induced charge depend on resistance. Now, what are the methods which can produce induced EMF? Number one, by changing magnetic field B. Now, magnetic flux phi can be changed by changing the magnetic field B, and hence EMF can be induced in the circuit as done in Faraday's experiment, which we have discussed this in the first video. 2. By changing the area of the coil available in magnetic field. Magnetic flux phi can be changed by changing the area of the loop A, which is acted upon by the magnetic field, and hence EMF can be induced in the circuit. Now you can see I have taken magnetic field. Here the direction of magnetic field is into the plane of the paper. Let's imagine a rectangular coil PQRS. Now I am going to move the rectangular coil inside the magnetic field. Now whenever the coil is moved inside, the area with which the flux is linked is going to change. So the loop PQRS is slided into uniform and perpendicular magnetic field. The change in area of the coil under the influence of the field is dA in a time dt. This causes an increase in magnetic flux d phi. So not only by changing the magnetic field, but by changing the area of the coil also we can induce the EMF. See the expression. So d phi is equal to b dot dA. Now what is dA? dA is nothing but area of the coil. Area can be represented as length into distance traveled. Here P dash S dash is the length. What is the distance traveled? That is from S to S dash. How can we determine the distance? Here the coil is moved with a velocity v in a time interval of dt. So simply use the formula distance equal to speed into time. So the distance between S and S dash is v into dt. So what will be the area then? That is L into v dt. So PLV dt. Now EMF E equal to minus d phi by dt. Substitute the value of d phi, that is BLV dt, in the expression. So you're going to have E equal to minus BLV. The induced EMF is due to motion of the loop, and so it is called motional EMF. If the loop is pulled out of the magnetic field, then E equal to BLV, because we are moving the coil outside, opposite to the first one. The direction of induced current is anti-clockwise in the loop, which can be determined by Fleming's right hand rule or Lenz rule. According to Lenz rule, the direction of induced current is such that it opposes the cause of changing magnetic flux. Here, the cause of changing magnetic flux is due to motion of the loop and increase in area of the coil in the uniform magnetic field. Therefore, this motion of the loop is to be opposed, so the current is setting itself such that by Fleming's left hand rule, the conductor arm PS experience force to the right, whereas the loop is trying to move to the left. Against this force, mechanical work is done, which is converted into electrical energy, which is called as induced current. Note, if the loop is completely inside the boundary of magnetic field, then there will not be any change in magnetic flux, and so there will not be induced current in the loop. Remember this point. Fleming's right hand rule. How can we determine the direction of induced current by using Fleming's right hand rule? Remember, Fleming's left hand rule is used to determine the force acting on a current carrying conductor, whereas Fleming's right hand rule is used to determine the direction of induced current. Stretch your three fingers, that is your thumb, the forefinger and the middle finger, such that the forefinger represents the magnetic field, the thumb represents the force, and the middle finger represents the direction of electric current, which is nothing but induced current. If the central finger, forefinger and thumb of right hand are stretched mutually perpendicular to each other and forefinger points to magnetic field, thumb points in the direction of motion, that is force, and central finger points to the direction of induced current in the conductor. Third one, by changing the orientation of the coil theta in magnetic field. Magnetic flux phi can be changed by changing the relative orientation of the loop with the magnetic field, and hence EMF can be induced in the circuit. The magnetic field, which is uniform. Now there is a coil, it is a rectangular coil. Now I am going to rotate the coil. So whenever I am going to rotate the coil in clockwise direction, that is a normal, and both normal and magnetic field are separated by an angle theta. So flux can be represented as NBA cos theta, where N represents the number of turns of the coil, B magnetic field, A area of the coil, theta is the orientation. At a time t with angular velocity omega, theta equal to omega into t, which we have learned in class 11 in angular kinematics. At t equal to 0, loop is assumed to be perpendicular to the magnetic field and theta equal to 0 degree. That means whenever the rectangular coil is perpendicular, both normal and magnetic field will be in the same direction. Phi equal to NBA cos omega t, because theta is nothing but what? Omega into t. So differentiating d phi by dt equal to minus NBA. Now derivative of cos omega t is minus sin omega t and derivative of omega t is omega. So the total expression will become d phi by dt equal to minus NBA omega into sin omega t. Now as E equal to minus d phi by dt, if you substitute the value of d phi by dt in this expression, you're going to have NBA omega sin omega t. Now here this NBA omega is called E naught, which is the maximum EMF. The EMF changes continuously in magnitude and periodically in direction with respect to time, giving rise to alternating EMF. Now here theta is nothing but pi by 2, pi, 3 pi by 2, 2 pi and so on. So once you are going to get 2 pi, one rotation is completed. Pi by 2 stands for t by 4, pi stands for t by 2, 3 pi by 2 stands for 3t by 4 and 2 pi stands for t, which we have learnt in waves topic in class 11. That is a wave which is going to represent, and E naught, that is the highest peak, which represents maximum EMF. If initial position of the coil is taken as 0 degree, that is normal to the coil is at 90 degree with the magnetic field, then theta becomes theta plus pi by 2 or omega t plus pi by 2. Therefore, E will change as E naught cos omega t. That means in place of theta, you have to substitute theta plus pi by 2. So sine of pi by 2 plus theta is nothing but what? Cos theta. Or sine of pi by 2 plus omega t is nothing but what? Cos omega t. Now for this expression, we can represent the curve as this is cos curve. The first one is sine curve, the second one is cos curve. You can see there is a phase difference of pi by 2 because sine curve starts from 0 but cos curve starts from maximum. So there is a pi by 2. Any one expression you can consider, either sine function or cos function, both represent sinusoidal wave alone. So alternating EMF and consequently alternating current can be expressed in either sine or cos function. This method of induced EMF is the basic principle of generators.